All right. Hi, everyone. Welcome to the next CPPC seminar. So today I'm delighted to introduce Juehang Qin, who's from Purdue University. Juehang is a graduate student working in Raphael Lang's group on the xenon experiment, but also a new and very exciting experiment called Windchime, which aims to detect dark matter in a kind of completely new and novel way. So I've been quite excited by this experiment since I first heard about it a little while ago. So I reached out to the collaboration to ask them to send somebody to speak on behalf of them. So that's Juehang, and thank you very much for I guess staying up to come and speak to us. And I'll leave it in your hands. Thanks.
Thank you for the introduction. It's really great to be here. And actually it's not that late yet, so it's still good. Today I'm just really excited to be here to talk about the Windchime project. So first I would like to go into a little bit of introduction about who we are. So very new project, right? It really only started a couple years ago, but the collaboration is actually rapidly growing at this point. And as you can see, it's we have included many groups right now. We have experimentalists working on the sensor development side. We have some people like me from more of a particle physics background, and my involvement because of my particle physics background is more towards the analysis, simulations, etc., that side of things. And we also have a good number of theorists in our collaboration, actually, which is really nice, really exciting to generate new ideas and think about what kind of maybe new models we might be sensitive to, that type of stuff. So generally, the structure of my talk is first, I would like to go through a bit of introduction. I wouldn't be focused on the standard dark matter introduction so much. I would like to focus more on kind of motivating how this experiment is designed and trying to give some intuition behind the concepts behind this experiment and what we're pushing towards, because this is a relatively novel idea. So I would like to try to motivate that a little. After that, I would talk about some of the existing stuff that we're doing, both in the hardware aspect with sensor development and so on, and in the software aspect, the analysis strategy and etc. And as I will talk about later, there's actually a lot of challenges for both, which is really exciting if you're a physicist, but also it means there are a lot of hurdles to get to where we want to get to. And these are challenges that we'll have to face. And finally, I would like to go into something a bit different, which is ultralight dark matter, which is, whereas the rest of my talk is mostly going to be focused on heavy dark matter. So first, even though I said I didn't want to get too much into dark matter, I just wanted to establish kind of a baseline. We are looking for dark matter, and we think there's dark matter out there. At this point, there's a lot of independent pieces of evidence for dark matter. There's the cosmic ray microwave background. There's the galaxy rotation curves. There's the bullet cluster, and even some stuff that I couldn't squeeze onto this slide because it's very crowded at this point, such as nucleosynthesis and so on. So we really believe that there's dark matter out there. Because of all of the independent pieces of evidence that don't even come from the same channels, we're quite sure there's dark matter out there. However, we're not so sure about the composition of dark matter. The thing is, if you're not sure about the composition of dark matter, it becomes very difficult to detect dark matter. Many detection mechanisms are in a very model-dependent way. I rely on the specific mechanisms by which dark matter couples to the standard model physics that we are all used to. However, it just so happens by sort of a numerical coincidence of sorts that it may be possible to detect dark matter through gravitational acceleration, through gravitational interactions alone around the Planck mass. And I say this is a numerical coincidence because at the Planck mass, particles start to become heavy enough that you can barely maybe detect the gravity if it's speeding past the sensor. And just to give kind of sense of scale, the Planck mass is approximately 20 micrograms. So it's quite small. It's, I think, about a grain of sand, but it's still a macroscopic kind of mass, as opposed to something that's more in the particle physics realm. So I hope that gives a bit of idea. So you can see maybe it is possible to detect that gravity. It's small, but not impossible. And it also so happens that because we know the dark matter density in our neighborhood, which is 0.3 GeV per centimeters cubed, with this kind of dark matter density and the known dark matter flux, at roughly the Planck mass, we would expect one event per year in an experiment with a cross-sectional area of 1 meter squared. So about one event, I really mean one dark matter crossing per year. And so it also means that the Planck mass is about as high as you can go with a reasonable experiment size, just in terms of the physical size of an experiment and how long you can push the exposure for. You can go up maybe one order of magnitude, maybe a tiny bit more than that, by having really big experiments, really long exposure times, but it becomes exceedingly difficult to go beyond that. And these confluence of factors tell us that we might be able to detect dark matter at the Planck mass via gravitational accelerations alone, via gravitational interactions alone. And what's also really exciting is that if we just, give it a bit of thought, at a very basic conceptual level, a nice place to look for dark matter might be energy scales where we do expect new physics. And the Planck scale is definitely one such energy range where we do expect new physics. And so because of that, there's kind of this happy coincidence where we can find dark matter in this mass range, or we believe that it's theoretically possible at least. And at the same time, it is interesting to look in this mass range. And this is also a relatively well-motivated parameter space that already has a few examples of models such as primordial black hole relics, which is one of my personal favorites. I think it's just conceptually it's a really attractive model, and also WIMP-Zealous. On this picture, I also highlighted the very low energy range, and that's because we do expect an experiment that is looking for Planck mass dark matter via gravitational interactions to also be sensitive to the low range, but the detection mechanism is going to be different, which I will elaborate on in a bit. So first, I would like to show kind of a video of how we would expect to detect dark matter. So at a very basic level, really what we want is a big array of very sensitive accelerometers. And so what happens when you have a big array of very sensitive accelerometers is if a particle passes through it, specifically a dark matter particle, it would create a series of disturbances which we hope to detect. And these disturbances, we hope to be able to detect it purely via the gravitational coupling, though that is more of a long-term goal than something we expect to achieve in the short term. So the general sensing paradigm for a single sensor is that we would have a test mass. This test mass essentially is just something that responds to gravity. And we would hold this with either a physical spring or a magnetic trap. And I will elaborate a bit more on why I'm talking about two different technologies here. And the general idea is actually really simple. It's just Newtonian physics. You have a force that is gmm over r squared, or r cubed times the vector if we're talking in vector notation. And this force essentially happens over a very short period of time, because we know dark matter roughly has a velocity of about 200 kilometers per second. And so the readout, on the readout side, there are a few possibilities. And at this point, at least, we are still, we are hoping for redundant readouts, because from experiencing other experiments, it's shown that it's very helpful to have multiple readout systems, because it kind of helps you cut down on experimental artifacts in your experimental setup, detector artifacts, so to speak. And so that this is essentially the general idea of what we want to do. So now I would like to go into a bit of intuition regarding the kinds of measurement noise we would face, to also motivate some, to also kind of point out what directions we want to work towards. And so one major source of noise is shot noise. At a very rough level, one can think of shot noise as essentially the noise that comes from Poisson statistics. It comes from photon counting. Now, this is a very rough classical view. There are ways to beat shot noise down using quantum technologies, which is something we would need. But this classical view does give us some important intuition. What it tells us is essentially the vertical level of shot noise is, or the power contained in shot noise, changes with laser power. When you have more laser power, you have less shot noise, because you're getting more photons, so there's less uncertainty in photon counting, essentially. One feature in this noise spectrum is that there's a big dip at the mechanical resonance frequency. This is kind of counterintuitive. We don't expect shot noise to, or rather we might ask, why does shot noise care about the mechanical resonance frequency? That is actually just due to kind of how this plot is made, and the y-axis of this plot, because this is in units of force, PSD, Newton squared per Hertz. Because this is units of force per frequency, if you have noise that is essentially flat in other units, when you convert it to force, your sensor is more sensitive to force at this frequency, because it is the resonance frequency. So it appears as though there's a lot less noise. These are kind of all correct, but different ways of viewing at the noise spectrum. And this is the most useful way to think about it for us, because we have a relatively flat broadband signal. And so two other major sources of noise that we have to worry about would be thermal noise and back action. And so back action kind of also correlates with laser power, but in the opposite direction. When laser power goes up, back action also goes up. And thermal noise in these units of force or acceleration, either way it's the same, it's essentially flat. So we think of it as white noise, and it scales with the mechanical quality factor, which is essentially how undamped your oscillator is, and also the resonance frequency. And one feature here to note is that there is kind of a knee here. So this does correspond to the optical cavity loss rate. And so some of the more complicated details in your cavity design and things like that come into play. And so on top of this, we can overlay our signal. The signal, as mentioned earlier, is essentially very flat and broadband. And actually, this signal shape is very easy to understand intuitively. The reason why it's effectively flat until some cutoff frequency is because what we have is a dark matter particle zooming by. And so if you're looking from the perspective of a low frequency measurement, this is essentially a direct delta. It is much faster than a lower frequency, like hundreds of hertz and so on. And so from that point of view, what you get is a flat spectrum because the Fourier transform of a direct delta is flat. However, there is a cutoff timescale for this signal, and the cutoff timescale is simply given by the distance, the shortest distance between your dark matter and your test mass divided by the dark matter velocity. So in this case, well, we know dark matter velocity at around 200 kilometers per second. And so if you work out the math for something in the millimeter or centimeter scale, this is roughly the order of magnitude that you would expect. So that's the introduction. I hope I did manage to motivate a bit of kind of which directions we need to push to really reduce the noise floor and improve the sensitivity. So now I would like to talk about sensor development, what has been done so far, really on the hardware side. And so I have to talk about five main hardware challenges. One of the biggest challenges we face is, as I mentioned earlier, just to get the noise down. And quantum noise is very important for us here. We want to really push both squeezing and back action reduction. And in fact, a large amount of squeezing and back action reduction is probably required for something like this to really work. And on top of that, we still need more scale. And the reason for that is even with all of the quantum noise reduction and back action reduction, we do not expect it to be, we expect it to be very difficult to detect a signal from a single sensor. We need the square root n enhancement from having a large sensor array. In addition to the fact that we are just talking about a particle which has a really low flux anyway, because at these high masses, we just have very little flux from the measured dark matter density. And so for both reasons, we just need very large sensor arrays. We also need environmental isolation. This aspect is relatively self-evident. If there's any seismic noise leaking in, etc., it would, of course, completely overwhelm any signal. We do need to reduce the thermal and Brownian noise. And by Brownian noise, I'm just referring to noise that comes from the ambient gas in whatever environment the sensors happen to be in. This is driven by temperature, mechanical quality factor, and of course, the pressure of the ambient gas. So the better vacuum you have, the lower these noise sources go down. And finally, not quite as obvious at first glance, it is actually a major challenge to just have data acquisition from a huge array at a very high data rate. We need a very high data rate because, as I mentioned earlier, our sensor is very broadband, our signal is very broadband, and it's only really expected to fall off at very high frequencies. And because of that, you just need to have a sampling rate that's high enough that your Nyquist frequency is above the cutoff frequency for your signal, so you're not losing any information. And so all of these are some main challenges for us. And how are we working on that? So one of the main things we're doing here, actually, this is work by the Oak Ridge group. And here, what they are trying to work on is really just the squeezing aspect of it. They have demonstrated 3 decibels of noise reduction via squeezing in an atomic force microscopy environment. And what they have essentially is a non-linear readout, and they've designed it in such a way that it's almost a drop-in replacement, which I think makes life a lot easier for everyone else to integrate it into their systems. And on top of that, there one other group, this is work from Gerard, who is part of our collaboration. What he's working on is levitated superconducting setups. And so he's actually working on both a larger setup, which is this picture here, and a chip setup, which I will talk about on the next slide. On this large setup, actually, he has achieved very, very good sensitivities and a quality factor that's quite astonishing to think about. So for reference, a quality factor of 10 to the power of 7, the reason why it's really important to us is because it represents the better your quality factor, the less you're affected by mechanical thermal noise. But on top of that, having a really, really good quality factor, what you see in the data that he has is that you can actually measure the ring down from a signal from a large signal, of course, for hours to days. And to me, that is actually quite astonishing that you can just kind of trap something and measure it slowly ringing down from an impulse for such a long period of time. Though, of course, in terms of sensitivity, what it really does is it allows us to kind of push the fact that it's less coupled to the mechanism that is holding it. This maglev setup, the really nice thing about maglev is that when one says maglev outside of physics, we think of trains. Right? Maglev is actually a technology that can levitate really big objects. And so there is potential for milligram scale masses or even bigger in this kind of trap. And the other really nice thing about maglev is that if you put a magnetometer in there, you can read out the position just based on the magnetic field changes. So that setup has really, really good sensitivity. But one of the things I mentioned earlier is that we need scale. So this is another setup that Gerard and collaborators are also working on. And here, the idea is to use a chip-based setup to kind of push to make it possible to mass produce and make a lot more of these. And the hope is that we can combine lessons learned from working in these different directions and come up with something that combines the really good sensitivity of the large setup and the scalability of the chip setup. A different direction that we're working on in sensor development, and this is done at Purdue, but not by my group at Purdue. There is actually also a second group at Purdue that is part of the Windchime project, the PI Sunil Bave, and what they are working on is MEMS sensors. So this is a bit of jargon. It stands for micro electromechanical systems. What MEMS sensors are is essentially, this is a way to fabricate sensors using photolithography and related technologies. So because of this technology is something that already scales. For example, all of us have a smartphone. Inside a smartphone, there is probably a MEMS accelerometer. What they do is they create really, really sensitive MEMS accelerometers. The idea is because we have this other technology that also scales up, this is firstly some risk mitigation in that we do have alternate technologies that we are pursuing at the same time. And so we don't have all of our eggs in one basket. And on top of that, one really nice thing about MEMS sensors is at the early stages, we can actually get more redundant readouts because this MEMS sensor already has redundant readouts. You can read it in a free space interferometric setup. You can also read it with a fiber-coupled laser. And right now, there are some ideas floating around where maybe we could try levitating MEMS sensor and see if we can learn anything by doing that. And finally, this is kind of the last, this is related to the last hardware challenge I mentioned, which is just data acquisition, essentially. One thing we're also working on is just evaluating our data pipeline, our analysis framework, and trying to figure out if there are any pitfalls that we just haven't thought of because we don't have experience running a huge array of accelerometers. And to kind of figure this out, what we've done is essentially just buy some commercial accelerometers, put them together, and read it with NI National Instruments digitizer. Right now, we're working on kind of a proof of concept dark matter limit. This is not really intended to be competitive because we're just using commercial accelerometers from ADXL. These are things you buy off the shelf. The idea really is to make sure that we do actually have the data pipeline, the analysis pipeline to, well, push through a dark matter limit. And in addition to that, the digitizer we're using is FPGA. So that actually allows us to maybe investigate different trigger strategies for heavy dark matter. Triggering for heavy dark matter is actually a big challenge, which I would illustrate why soon in the following slides. And we can also kind of test different data acquisition strategies. And this is because when you have a built-in FPGA, you can kind of code into the digitizer and play around with that. So that is kind of all of the, a quick overview of the hardware efforts that we're working on. And so now I would like to go into some of the software, the analysis side of things. And once again, there are a few key challenges that we have to face. The biggest key challenge for us is recovery of small signals. The key problem here is that the signals are below the single sensor noise level, or we expect them to be below the single sensor noise level. It's what we expect to need to really push our sensitivities to the point where we think we can get to the gravitational coupling. Because it is a very hard problem, and we really need to, we need to squeeze every last bit of juice out of our data. There is a problem with that. There are two problems with this. First, on the inference side, it just makes inference difficult because now you have to do inference directly on your huge data set, and you can't do the typical thing we like to do in particle physics, which is, you know, take this really high level, really low level data set and convert it into high level data sets and never really look at the low level data set once we've done that. The other issue is with triggering. We can't trigger on a single sensor anymore because we expect signals to be below the noise level if we look at any individual sensor. And so that once again presents a big issue, and that's something that we will need to really think about and work out. The second issue is, actually a repeated issue from the hardware side. We do have a huge data rate. And of course, as expected, this is an issue for analysis as well, just due to the computational requirements and so on. And this issue actually leads to issues 3 and 4, where we have a really complex problem. And we really don't want to have to do a big Monte Carlo, especially at this stage, because we don't have the computational infrastructure for this Monte Carlo. We don't put the cart before the horse and invest a huge amount in computing infrastructure before we have the sensors, especially for such a long-term project. So how do we essentially figure out what the look elsewhere effect is without doing 2MCs? Or without doing too many 2MCs. And this is actually a critical issue that informs our sensitivity, because the look-elsewhere effect tells us what kind of thresholds we can set for signal-to-noise ratio if we're doing template matching, for example. And on top of that, it also makes reliable sensitivity estimates difficult, because the easiest way to get a good sensitivity estimate that's not a back of the envelope without a lot of approximations going into it is to just simulate some data and analyze it. But that will be a huge amount of effort because of the computational requirements of such huge data sets. So these are all challenges that we're dealing with right now. So to go into a bit about what's already been done so far, this is one example of what data might look like from a large accelerometer array. The top row is what you would see in real life. If you didn't simulate this data, you wouldn't really be able to see much. It would all be buried in noise. But on the bottom row, we can see the Monte Carlo truth. There is some data buried, there is some signal buried in there. So can we recover it? This is a different view of the same problem. We can see from the video that you can't really, all the sensors are kind of flashing around on the left, which is what you see in real life with noise. But on the right, let me just play the video again. On the right, you can see that there's a nice correlated signal going through. And that kind of gives us a strategy on how to deal with it. What we could do is template matching, but instead of doing template matching on individual sensors, we do template matching in this nice time correlated manner, because for a given track, we know what the time correlations are. And so instead of checking every sensor for every possible peak, we are looking for all possible tracks within some parameter space. So tracks within reasonable dark matter velocities and so on, for example. And if we do that to the data that I showed on the previous slides, we find that we do actually recover a reasonable signal. What we find is that actually even with a signal that's so far below the noise level, if we're looking at a single sensor, we can get an SNR of about 8. And we actually also recover the parameters reasonably well. The truth parameter or the Monte Carlo truth value is indicated with the red X. You can see that the maximum in both the velocity and time space or the geometry essentially indicating where the track entered the array, both are recovered relatively well. And these are not all of the parameters that we are inferencing, of course, because the track isn't determined just by 2 geometry variables. There are actually 2 more geometry variables. But these are just 2-dimensional projections to show that, yes, we actually can recover these signals. Another thing we are working on is also a Bayesian approach. And here we're using UltraNest. And the nice thing about the Bayesian approach is, firstly, the optimization or the minimization aspect is kind of built in. With a template matching approach, you have to kind of look for the maxima or the maxima of SNR. And that is not necessarily easy if you have a large data set, if you really want to try to analyze a really large array, because it's very computationally intensive. Previously, what I showed is essentially just a grid search, and that is possible with the simulated data, which is only a small 4x4x4 array. But as that scales up, it becomes more and more difficult. So you do need to look into optimization algorithms to try to home in on that the true value and the peak in SNR without having to search the entire parameter space. With this Bayesian approach, it's not so much a real, like a computational shortcut as it is, I guess, a research shortcut at nest assembling or Markov chain Monte Carlo. These approaches, they already do it for us. So it's something we don't have to worry too much about as of now. And on top of that, one really interesting thing is that Bayesian approaches can actually be used to estimate the look elsewhere effect. And there's this really nice paper here that describes how to do that. And this gives us a first estimate of what our look elsewhere effect is. And even if it's just the order of magnitude estimate, it already helps a lot in figuring out what kind of thresholds we need to set for our SNR. Some other things we're working on here include trying to get sensitivity estimates by, instead of doing a huge Monte Carlo, we can do a simple TOIMC, just looking at all of the impact parameters, which the impact parameter is the term for describing how close a track passes to a sensor, essentially. So that's relatively easy because we can just have a grid of points and calculate how far random tracks get to sensors in that grid of points. And on top of that, we can do some frequentist estimation of the look elsewhere effect. And that's also something we want to look for. And I mentioned the look elsewhere effect over and over again because I think the way to think about this is kind of similar to LIGO, where we really need to be careful about what is the false positive rate. And so this is something that LIGO worries about a lot as well. And we expect that this is something we really have to worry about. So with all of that work into hardware and software, where do we think we would be in the near term, right? So in the near term, which is this orange line labeled 2x2x2 sensor array, we expect to be about here. And so this shows that we are covering some new parameter space, but this is also kind of a parameter space, I think, that people are usually not used to thinking in. So what does this actually mean, right? How interesting is this? Well, in reality, we're still many, many orders of magnitude away from what we expect the gravitational coupling strength to be. And I do want to mention also that this plot is still quite preliminary right now. And a lot of the sensor parameters and so on, they're still quite subject to change. So it should be viewed kind of as a rough guess of where we think we would be in the near future. And of course, the Windchime vision line is just where we hope to be in the distant future. It's not really a projection. So what is this parameter space? Essentially, on the y-axis, I am just assuming that there is some kind of arbitrary long-range force that has a coupling strength alpha to nuclei. And so n is just a number of nuclei. And so what we have here is alpha is really just g. For a gravitational force, alpha would be g times the dark matter mass times the mass of a single atomic nuclei. So for any given atomic nuclei, we can plot what the gravitational coupling strength will look like in this parameter space. And for lead, it is the green line here. And so as I mentioned earlier, we're still many, many orders of magnitude below. But even though we are very far away from our final goal, we can already start probing in this novel parameter space. And on top of that, there's actually more. So far, I've only talked about heavy dark matter for the most part. We do expect to be sensitive to light dark matter as well. Here, I would focus on what is called B-L dark matter, and the idea is quite simple. It is dark matter that couples to this new quantum, this new charge, which is just a baryon number minus the lepton number. This is attractive for a few reasons. It's a very simple model. It's just a spin one vector field, and this coupling is allowed by the standard model with no new gauge anomalies, so it's relatively easy to introduce as well. And with ultralight dark matter, when the dark matter mass is very low, because of the local density, the occupancy is really high. And so the dark matter would appear to be a plane wave incident on a sensor. And the line width is essentially just given by the velocity dispersion. If dark matter is all kind of the same velocity, then there wouldn't really be a line width. In our case, the line width corresponds to about 10 to the minus 6 times the frequency, which means, let's say, if you have a megahertz signal, then your line width will be 1 hertz. So we are talking about a signal that is pretty monochromatic here, and we can approximate that to be essentially just a sine wave that we see in our sensors, a correlated sine wave that you see in every sensor, because the coherence length is also really long and the wavelength is really long. And that's what the signal model will look like. Essentially, as I mentioned, you just have a force that is sinusoidal in time, and it's really that simple. And that is proportional, of course, to your coupling strength and a B minus L charge. And it happens that for neutral materials, so essentially anything we have that we are not charging up on purpose, the B minus L charge is really just the neutron number, because the proton number and the lepton number are completely balanced out. So the only balance you have are the neutrons. And so what you have, if you convert that into acceleration, so you just divide everything by the mass of your sensor, is that you find this acceleration signal is actually just material dependent. So that's really nice. It doesn't depend on anything else except for coupling. This A naught, which is in natural units, is equal to just the square root of the dark matter density locally, and this material dependent factor. And this is material dependent because A and Z are just properties of the elements the chemical elements that make up your sensor. And when you have this kind of signal that's material dependent, what you can have is two different sensors that are trapped the same way, and they experience the same coherent wave. And you can have a differential readout where you subtract the signal between the two. So this allows us to subtract any backgrounds that might happen to be correlated, such as, for example, imperfect environmental isolation, allowing vibrations from the outside to leak in. We would expect that to be correlated for the two test masses, and that allows for much easier measurement. And with ultralight, this is kind of the type of measurement we hope to be able to make. And with that kind of measurement, this would be the approximate sensitivity that we hope to achieve in the near future. Of course, I should note that even though earlier I mentioned that the maglev setups are tunable, the actual amount of tunability, it really varies on the final construction. So I want to say that these are not this is not kind of a prediction that we will have 3 or 4 orders of magnitudes of a tunable sensor. But the idea is essentially, if we have a sensor that it has a resonance frequency of about 100 hertz, this is a sensitivity curve that we expect. And if we're using the maglev technology for a given sensor, we expect to be able to move this peak left and right somewhat as well to cover a bit more space. So the key takeaway, I think, or the key takeaways, plural, would be that we are, a very recent collaboration, but we've been all working on kind of trying to make this happen and trying to push new ground in these parameter spaces. And we actually hope to do that as well in the relatively near future. And I personally, I think it's very exciting, and I hope everyone thinks that it's very exciting too, to be able to cover all of this new parameter space. Thank you.
Thank you very much for that very interesting seminar. Do we have any questions from the audience? You got an applause.
Thank you.
Okay, while people are thinking, oh, Teresa, do you want to go ahead?
Yeah, thank you for this really interesting seminar. Just in terms of timescales, is it a couple of years when you say near future? Is it 5 years? Like, kind of, what do you think is kind of the scales there?
Yeah, so for me, I think it's a bit difficult for me to give a timescale. I think a big part of that, to be honest, is just because I'm a graduate student, so I'm not really aware of the funding stuff that's going on behind the scenes. Behind the scenes to me, anyway. But this is stuff that we are actively talking about and working on. So yeah, I guess that's what I can say. It's stuff that we're actively talking about and working on, and it's not just kind of super far out, completely on the drawing board kind of thing.
Yeah, and I guess technology-wise, it would be fairly doable. Like, if the funding's there, you could build something.
Yeah. For the near-term stuff, what we're doing is technology that I think to some extent exists in the collaboration, and we need to put all of it together.
All right, thank you.
Glenn? We can't hear you, Glenn.
There we go. Thank you for the talk. It's very interesting. I just had a question about your 2x2x2 sensor array on the plot you've got there. Is that using commercial accelerometers? And if so, what is the sensitivity of those in G's per hertz?
No, we would actually need maglev setup for that.
Okay.
Yeah. And
do you know what the acceleration sensitivity is for those? You mentioned, I saw Atto G's in one of your later slides. I wondered if that was kind of the order of magnitude you were shooting for.
For the long term, Atto G's is what we're shooting for the long term. So yeah, I don't remember the numbers off the top of my head, but what I remember is I think Atto G's is kind of the range we would expect when we are getting close to the gravitational coupling. So we should be still clear of that. Okay,
I see. And just one other question. So you're modeling this interaction as an impulse. Is that right, on each mechanical oscillator as the dark matter particle moves past each oscillator? And so you're looking at the resonance frequency of the mechanical oscillator. Is that correct?
So we are modeling it kind of as an impulse. But actually, the funny thing here is the typical intuition for sensing kind of doesn't work, because the signal frequency is so high that it doesn't really matter what your trapping is. It almost always behaves like a free space sensor. So because your signal is 10 to the 8 hertz or something like that, or 10 to the 7 hertz, and your trapping frequency is 100 hertz or 1,000 hertz, or even 10,000 hertz. So what you end up having to do is to kind of differentiate to get your acceleration signal out. You wouldn't really be sitting on the resonance frequency for very long. The other thing about the resonance frequency is just the longer you integrate, the more thermal noise you integrate over. And because we are pushing the sensitivities really far, for the longer term, I don't think it's so much of an issue in the near term, but for the longer term, we wouldn't be able to integrate for such time simply because we'll be overwhelmed by thermal noise.
Okay, thank you.
Michael?
Yeah, thank you for the very interesting talk. So since any individual sensor is always dominated by noise and you need the correlation, so you're actually using the velocity that you more or less know, but wouldn't also the directional information also help? Because there are directional detection experiments in the making, right? So I would guess that that would help you to correlate your signals from your different sensors.
Yes, indeed. We do hope that the directional information would be helpful for our sensitivity. For now, I think it's not really taken. We are not taking full advantage of all of that information in our analysis side of things. But in the long term, I think if you can observe, because this is a naturally directional detection mechanism, if you can observe like the daily modulation or the annual modulation and the directionality of that, I think that would really help, and it would help distinguish dark matter from other things, essentially.
All right, thank you.
Any further questions? If not, I can go. So I'm just trying to get my head around this plot on the left-hand side. So this Windchime vision, what is the configuration of that in terms of like the size and the length of time that is assumed?
Yes. So what I meant earlier when I said we shouldn't take that too seriously as a projection is the vision is really kind of aligned where we would like to go. So it's not really backed by a physical configuration like the 2x2x2 projection is. Though the vertical line, we could, this essentially just corresponds to a few meters squared years worth of exposure.
Yeah,
so
that's so I think, yeah, so which mass that vertical line goes up is basically just depending on how much flux you're able to capture, right? So the size.
Yeah,
okay.
yeah.
And then the gravitational coupling of lead. What is that? Just a coincidence that or is that just a choice that you've made to how precisely you want to be able to measure these forces? Or
that's the choice. That's where I drew the line, essentially.
Okay. Yeah.
Because we want to detect gravity.
Okay. Yeah. I think I've got it. And is that same sort of case for the right-hand panel for the B-L, or is this a more shorter term type of experiment which wouldn't need to be so large?
The B-L is a shorter term, and I believe the lines correspond to 2-month exposures.
Mm-hmm.
So I think the kind of the understanding of the B-L lines is the reason why it looks really good is because we are effectively sitting on a resonance frequency and drilling really far down instead of for like weeks to months instead of doing a broadband search. Did
you consider also like a scalar, like a dilaton like model as well for like an scalar, or are you just not sensitive compared to kind of the force experiments or something? I think essentially we should be sensitive to any long range force that that just provides some kind of acceleration signal that we see. So I think we should be sensitive to that, but off the top of my head, I don't know if it would be competitive. Mm-hmm. That's probably something we'll just need to try out. So let me give the opportunity for the audience again to jump in if they have any questions. So if not, maybe Michael, do you want to go again?
Yeah, I guess an obvious first limit that you could set would be on extra dimensional gravitational interactions, right? So that would be easy.
Would you mind elaborating a bit on how, like, what kind of signal one would expect with that?
Well, it would just be stronger gravitational interaction than in 4D, right? So.
Okay, yeah, we haven't really looked at that, but thanks for the suggestion. I think I could try looking into that as well.
So maybe I'll ask one last, I guess, more specific question. Can you go back to your slide where you were showing you had your corner plot with where you're doing this Bayesian scan over all of these different parameters? Yeah. So there are 4 angles here. Is that like the income, the angle it comes in at and the angle it goes out at, or something? Or?
Yeah, I think I think I worked it out, and you just need 4 parameters of some kind to parameterize any track. And the 4 we settled on, just because it's mathematically easy to work with, is to have a bounding sphere on our sensor array, and one vector on the bounding sphere indicates the entry position of the track, and one vector on the bounding sphere indicates the exit. So that's kind of where the 4 angles come from.
Yeah, okay, that makes sense. Yeah. And what do you sort of, I mean, I know this is just a sort of toy model, but what would you assume for the sort of the geometrical shape of the whole thing? Would these, you had this little movie where you had this big cube of pendula. Would that be sort of how it would, in your sort of the far future vision, is that sort of how it would look, or would it be these sort of, would these just be placed randomly around some lab depending on whatever space you have?
I think for now we are mostly looking at cubes. We expect to need a relatively high packing fraction, or I guess however we want to call it. We expect it to need a tightly packed sensor array. So we haven't really experimented too much with the geometry of that yet. So far, all we've really looked at is how kind of our sensitivity scale with the spacing between the sensors. So how tightly packed we need it to be. But I do expect there would be influence on the sensitivity as well. And hopefully at some point we can optimize the geometry a bit more than a cube.
Yeah, it's quite interesting. And maybe I just want to ask you, what is what is ultra-nest? Because I've heard of multi-nest, but is ultra-nest like a really good version or something of multi-nest?
It kind of it is nest assembling like multi-nest. I personally just really like ultra-nest. I think so. I'm not an expert on this Bayesian stuff, so I'm not going to comment too much on like the correctness and that side of it. But what I really like about it, it works in Python and it's really fast. So, and it's very Pythonic. The documentation is really easy to read. So yeah, that's kind of the main reasons why I settled on this.
I have to give it a look. All right, so last chance for anyone. But if not, I'll stop recording now.